Okay, so we're moving into some graphing here, and we are going to alternate for the next little while. We'll do our 2 lessons each day. We're going to start with one that's focused more on the 052, 038, or an O2 level course, and then the second one focused on 053. We should be able to get through all of the material in. We've already covered everything that's in the O2 level courses at one point or other, and we should be able to get through everything that's in those other 3 courses as well, at least an overview of it. We don't do every type of question from every single section, but giving you the basic ideas. So this here is graphing. It's very much focused on the Math 053 Chapter 4. We're going to look at Section 4.1 right now. 026 and 038 do have some very rudimentary graphing. So understanding some of the beginning stuff here, what the x-axis is, what the y-axis is, how to plot points, and what the basic idea of when you look at a graph, what does it represent? What does it mean? That stuff is useful, but once we get into the nitty-gritty details, it's really only the 053s that this is applicable for. And again, for Math 052, there is actually not graphing specifically in your course, although there is some overlap here and there, and I'll mention when that happens. But really, other than getting an advanced look at how this all works for when you move on to 053, there's not a direct connection to your course there in these lessons on graphing. Okay, so all of Chapter 3, when we were solving equations, we always had just one variable in any equation. It might have appeared more than once, but it was the same variable, right? There might have been more than one x, but there was only x's. What we are going to start to look at now is what we do when we have 2 variables. We have 2 things we don't know in an equation. Usually, we tend to represent them with an x and a y, although theoretically they could be any 2 letters. And what we're going to discover is that a really helpful way to figure out those situations is to put those values as points on a graph. So yeah, we usually use x and y for these variables. And when we talk about an ordered pair, we're talking about an x and a y that belong together. They go together. Okay, there are actually multiple ways to graph points, but the only one we're going to look at here, and it is the most common one, is something called rectangular coordinates, or actually officially usually called Cartesian coordinates, named after Rene Descartes. You may or may not know of Rene Descartes. He's the I think therefore I am guy. So he was a philosopher as well as a mathematician. So there is a typical rectangular coordinate graph, and you see that we have an x and a y. This is called the x-axis. There I've highlighted in red. It's the one that is horizontal. It runs right and left. And on that x-axis, it's just like a number line. When you go to the right, it's positive. When you go to the left, it's negative. So that is the first variable, the x variable. And then in blue, I've got the vertical, which we call the y-axis, and you can see we usually put a little x and a y to remind ourselves on each one. And it's the same idea, except when you go up, it's positive, and when you go down, it's negative. And I think I might have to adjust my screen here. I'll have to remind myself of that. Yeah, I'm going to have to. Okay, all right. So when you go up on the y-axis, it's positive. When you go down, it's negative. The very, very middle point, 0, 0, where we haven't gone anywhere, we haven't gone to the right or the left or up or down, is called the origin. That's the point, 0, 0. And again, see how we put a pair that goes together in brackets, an ordered pair like that. So let's try putting some points on this graph. You can see I have my horizontal axis, the x-axis, going right and left, my vertical axis, the y-axis, going up and down. There's a point where x is 3 and y is 5. So what that means is I'm going to go 3 to the right and 5 up. So let's see over here. 3 to the right, 5 up. So there's the point right there. And there we see it appear. So there's 0.35. Here's one that has a negative in it. So x is -4 and y is 1. That means I'm going to go 4 to the left and 1 down. Sorry, I lied. 4 to the left and 1 up. +1, right? -4, so 4 to the left. +1, so 1 up. Right there, -4, 1. And there's a bunch more. Why don't you just take 30 seconds and look at those and just imagine where you think those are going to appear on the graph, just to make sure you got the basic idea down, and then we'll put those up there quickly and then carry on. Okay, 5, -4. So x is 5, so that means 5 to the right. Y is -4, so that means 4 down. So 5 to the right, 4 down. There's that point right there. -2, -3. So x is negative and y is negative, so we're going to go left and down. 2 left, 3 down, right there. 0, 3. So x is 0. That means we do not go right or left, but we go 3 up. So don't go right or left because x is 0. Up 3, right there. And the last one, y is 0, so we're not going to go up or down. We are going to go just 2 to the left, right there. -2, 0. Okay, so there's those points plotted on the graph. If x is positive, you go to the right. If x is negative, you go to the left. If y is positive, you go up. If y is negative, you go down. Okay, now you're gonna be asked about what quadrant points are in. So let's just take 20 seconds to talk about this. The quadrant where everything is positive, where x and y are both positive, so to the right and up, is called quadrant number 1. And then for reasons that you won't discover until you're in Math 073, we move counterclockwise. So that quadrant there is quadrant 2, down there is quadrant 3, and over there is quadrant 4. So just remember, you start where everything's positive and you rotate the opposite of a clock in order to label those 4 quadrants. So really quickly, let's identify which quadrant all these points are in. 0.35 we can see is in quadrant 1. -4, 1 here we can see is in quadrant 2. 5, -4 down here we see is in quadrant 4. -2, -3 is in quadrant 3. And then the last two aren't actually in a quadrant. 0, 3 is neither in quadrant 1 nor is it in quadrant 2. So we can't say what quadrant it is. What we can say is it is on the y-axis. And what we can say about -2, 0, again, it's not in quadrant 2 or in quadrant 3. We just say it's on the x-axis is the best that we can do for those. So there's just a little bit of terminology that will come up in some questions they ask you about. So being able to plot points using positive, negative, x and y, and being able to know what quadrant the point is in or if it's on an axis. Okay, so what we're going to do now is we're going to go through a little spiel about why we are even graphing to begin with and what that picture of the lines we are going to graph, what it actually means. What does it represent? Because I find that people can get all the way through chapter 4 and they can get all the questions right. They can draw the lines, they can calculate the equations, they can do all the things you're going to be asked to do. But when I ask them, so what does that line mean? They don't have a clue, which then causes a lot of difficulty with any kind of the understanding sorts of types of questions that can come up. So what is a graph anyways? So here is my one sentence answer to that question. A graph is the answer to an equation. It is the answer when there are 2 unknown variables instead of just 1. So what do I mean by that? Well, let's just remind ourselves when we had variables with only equations with only 1 unknown variable, like the ones you did in chapter 3. X plus 3 is 10. We know the answer to that is x equals 7. That is the only number that makes that equation a true statement. 7 plus 3 is 10. 8 plus 3 is not 10. 5 plus 3 is not 10. 142 plus 3 is not 10. Only x equals 7. There is only one number that makes the equation true. Yeah, only one number. So what happens if there's 2 things we don't know? Let's take a really simple one. X plus y equals 10. So there's an x and a y. Well, you can see that I kind of copied the setup of the last question. So one obvious answer might be the same ones we did last time. 7 and 3 works, right? Because 7 plus 3 is 10. That makes the equation true. Oh, good, we're done. No, we're not, because I'm sure you all can see that 7 plus 3 isn't the only option, because 5 plus 5 is also 10, right? 5 plus 5 makes the equation true. So x is 5 and y is 5. Or x is 2 and y is 8. That makes the equation true. 2 plus 8 is 10, yeah? 10 plus 0. Why not? Why can't one of the variables be 0? No reason it can't be. 10 plus 0 is 10, so x is 10 and y equals 0 makes the equation true. What if we turn these into a table? This is called a table of values, and there is all of the pairs that we already had figured out. 7 plus 3 is 10, 5 plus 5 is 10, 2 plus 8 is 10, 10 plus 0 is 10. So those are XY pairs that all make the equation true. But I'm sure you see by now that we could go on and on and on forever. We had 10 plus 0 makes it true, but so does 0 plus 10. Here's what I was going to say earlier. Who says they have to be whole numbers? How about 8.5 and 1.5? If x is 8.5 and y is 1.5, they add up to 10. That is a pair, a value for x and y that makes the equation true. How about fractions? I think I do next. Yep, 5 and a third plus 4 and 2/3. Add those together and you will get 10. So that is another xy pair that makes the equation true. How about really complicated decimals? Why not, right? 3.791132. If you add that x value to a y value of 6.20868, you will get 10. So that is a pair that makes the equation true. Now how about negatives? Yes. -2 plus 12 is 10. So there's another xy pair that makes the equation true. Or we could get really, really big numbers. 4,235 plus negative 4,225, those add up to 10. Okay, hopefully what you are seeing by now is that we could go on all day long. We could keep on going and finding thousands and thousands and thousands of xy pairs that make x plus y equals 10 true. So obviously just writing the answer like we did with an equation that had one variable and we said, oh, x is 7, done. That's not possible. We can't just state what the numbers are that makes this equation true, because there are billions of them, because there's 2 unknown variables. Somebody had the incredibly bright idea, or maybe lucky idea, to take these xy pairs and put them on René Descartes' graph, our rectangular coordinates. And for this type of equation, they discovered something very interesting. There are all those points plotted on the graph in the same way that we were just talking about, right? When x is 2 and y is 8, you go 2 to the right and 8 up, like so. And look at that. All of them sit on a straight line. All of the pairs of points we found that make the equation true sit on that line. And even, let's see, oh yeah, so even here I didn't actually plot the fraction one here because the program I used had trouble with fraction, just writing out fractions, but look, it's there too, right? Try that out. X is 5 and a third, so 5 and a third, right about there. And then y is 4 and 2/3, up 4 and 2/3 of the way to 5. Sure, it's right there on the line, just like all the other ones. Even points that we didn't find in our table of values are there on the line. So look at this one here. When x is 1 and y is 9, it wasn't listed in our table, but when we drew the line through the points that we had, 1, 9, does 1 plus 9 equal 10? Yeah, sure it does, right? So every point that is on that line makes the equation true, and every point that makes the equation true is on that line. And that is why I said that this line is the answer to the equation when there are 2 variables. Because we can't list all the numbers, but we can't list all the pairs of x's and y's that make the equation true, but we can draw all the pairs of x's and y's. And this line continues to the down and to the right forever and up and to the left forever. So it would ultimately go through any possible point that makes that equation true. So an equation with one variable, that's how we write the answer, x equals 7. An equation with two variables, we can't list the answer numbers, so we draw them. That is the answer to the equation x plus y equals 10. So that's our basic understanding. I think I'm going to talk a little bit more here. Yeah, so I'm just going to reemphasize any point that makes the equation true is on the graph. So let's just pick a random pair of numbers that make the equation true. 3.7 plus 6.3 equals 10. Yes, it does. That makes the equation true. And look, there it is on the graph. X is 3.7, right, over 3.7, and up 6.3, right on the line. Or vice versa, any point that is on the line makes the equation true. So there's a point that I see is on the line, negative 1, 11, right? I can find it there. Does negative 1 plus 11 equal 10? Yes, it does, right? Every point that makes the equation true is on the line. Every point on the line makes the equation true. If you feel like I've said that 15 times in the last 2 minutes, you are right, because that is the most important thing to remember about lines. They are simply a picture of the xy pairs that make the equation true. Okay, so the solution to an equation with two unknown variables can be represented with a picture, which we call a graph, showing all the points that make it true. Next question is, how do we go about finding points that are part of the solution, finding points that are on the line? And this is what we're going to spend a lot of time on in this chapter, finding different ways in different situations, the easiest way in different situations, the most useful way in different situations to find points that make the equation true. So one possibility is that we can just test pairs. We can just sort of guess at them, or maybe someone gives us some options and we can just check to see if they work. The second option, which is going to be far more useful, is that we pick values, any values we want for x, and then we find the y that goes with them, or vice versa, pick values for y and find the x that goes with them. This sort of, people struggle with this a little bit because they say, how come I can just pick any numbers I want? You can pick any of one of the numbers that you want, either the x or the y, and then you specifically find the other one that goes with it. So you pick an x, find a y that goes with it, or vice versa, and you will get a point that is on the line. So let's just do that first one, because they will ask you to do this. They will ask you to test points. So they'll give you a point and they'll say, is this a solution to that equation? So is 2, 3, so in other words, x equals 2 and y equals 3, does that make this equation here a true statement or not? And what you're going to do is you're going to take that x and that y and you are going to put it into the equation. So I'm going to replace the x with a 2 and the y with a 3, like so. And you'll see I put some question marks there because I don't know if this is a true statement, so I don't want to say they're equal. What I want to say is I'm checking if they're equal, right? So let's work this out. We got 4 times 2 is 8. 2 times 3 is 6. And then a 12 on the right-hand side. 8 plus 6 is 14. Does 14 equal 12? No, it does not. 14 does not equal 12. Therefore, no, the point 23 is not a solution. It is not on the picture of the line that shows all the answers to that equation. Is 4 negative 2 a solution? Same thing. Let's check when x is 4 and y is negative 2. So plug them into the equation for x and y. Replace the x with a 4 and the y with a negative 2. Question marks again because we don't know. We're going to see if that's true or not. 4 times 4 is 16. 2 times negative 2 is negative 4. So is 16 plus negative 4 equal to 12? Yes, 16 plus negative 4 is 12. So yes, 4 negative 2 is a solution. When x is 4 and y is negative 2, it does make this equation into a true statement. 12 equals 12 in this case. Therefore, the point 4, -2 is on the picture we draw, the line we draw, showing all of the answers to this equation. All right, so let's do option 2 here, because if we were just guessing and checking, that's going to take a long time to find points. So let's start by throwing the, let's use the same equation and start by throwing on the point that we already discovered in the last slide. We discovered that 4, -2 is a solution. We didn't really discover that though, right? I gave it to you and you tested to see if it is a solution. So let's see how we discover our own points. And what I'm going to ask you to do is I've just put some values there, and I want you, or we'll do it together, to find the y's that go with these x's and the x's that go with those y's. And if you're wondering where these numbers came from, I just picked them, right? Pick any number you want as long as you find the right y that goes with that x or the right x that goes with that y to make this equation true. So here's where if you are in 052, this actually still has some value, because we're going to do a bunch of basic equation solving, which, as we've already talked about, is something you do have to do in 052. So you don't need to worry about the graphing part of this, but if you want a little practice in your equation solving, this is useful. So let's take these one at a time. So I'm going to take that x equals 0, and I'm going to pop that in for x. And my goal is to figure out what y makes the equation true. And like I said, this is just equation solving. 4 times 0 is just 0. So I end up with the equation 2y equals 12. And I know how to solve that. I divide both sides by 2, because the 2's cancel. And I get the y by itself, which is the whole point. 12 divided by 2 is 6. And there I go. That is how you find your own solutions to points that are on the graph of a line, points that make the equation true. Check it if you want. Go back to the equation. So I'm claiming 0, 6, right? When x is 0 and y is 6, 4 times 0 is 0, plus 2 times 6 is 12. 0 plus 12 is 12. Yeah, it makes the equation true. Let's try the same thing with the 1. I simply put the 1 in for x, and then I solve the equation for y. 4 times 1 is 4. I'm going to subtract 4 from both sides. You can see I'm skipping those steps a little bit here, but there in the middle, if you want, is a step that says 2y equals 12 minus 8. A plus 4 on the left became a minus 4 on the right. Divide both sides by 2 to get the y by itself. 8 divided by 2 is 4. So there's another point. Again, we can check. 4 times 1 is 4. Plus 2 times 4 is 8. So 4 plus 8, sure, 4 plus 8 is 12. So the point x is 1, y is 4, makes the equation true. All right, let's switch it up now, and let's grab some y values and show that we could do the same exact thing backwards, where I give you the y and you plug it in and find out what the x is. So I put a 0 in for y. 2 times 0 is 0. So I simply have the equation 4x on the left equals 12 on the right. Divide both sides by 4, gets the x by itself. And so when y is 0, x must be 3. Try the other one. We're going to plug in a 2 for y, like so. 2 times 2 is 4. Subtract 4 from both sides. 4x equals 8. Divide both sides by 4, gets the x by itself. And there we go, x equals 2. Let's try that one too. Let's just double check. So I'm claiming that when both x and y are 2, then it makes the left side equal the right side. 4 times 2 is 8. 2 times 2 is 4. 8 plus 4, sure, is 12. So there is the first method we are going to develop in our next class for how to find how to draw the graph of a line. We are going to pick our own x's and y's, ones that seem easy, right? Notice I picked easy numbers here. I could have plugged in x equals 246.9173, and calculated the y value that goes with it. There is one. I could have done it. Why would I do that? I could have plugged in x equals negative 4 3/7 and calculated the y value that goes with it. Why would I do that? Pick nice, easy numbers and find the values that go with them. Those hard ones are on the line too, but why would you find a hard point when you can find an easy point? So now I'm getting a little bit ahead of what you're going to do in the first section, but now we could go ahead and put these on a graph. And there I've done that. Hopefully you can see that, but I took all of these points we found. So x is 0, y is 6. X is 0, so we don't go left or right at all. Straight up 6, there is 0, 6. X is 2 and y is 2. 2 to the right, 2 up. There's that one, right? X is 4 and y is negative 2. 4 to the right, down 2. There it is right there. So I took all those points, I put them on a graph, and as before, we see they all sit on a straight line like so. And our last thought for this lesson is I want to point out that, I want to ask a question actually. Before that, remember at the very, very, very start of this, when we first started with this equation, we tested 2, 3, and we found that it is not a solution. It made this equation into 14 equals 12, which is not true. Well, that means 2, 3 should not be on the graph. And sure enough, there it is, not on the graph, right? Any point that makes the equation a true statement is on that line. Any point that doesn't make the equation a true statement is not on that line. Every point on that line makes the equation true. Okay, now I'm going to ask a question. I plotted 5 points there. Did I need to plot 5 points in order to draw that line? Think about that. How many would have I needed to draw a line, a straight line? And hopefully you're thinking to yourself that the answer to that question is 2. And they could have been any 2, right? It could have been those 2 points. And imagine you have a pencil and paper and you get those 2 points, pick up a ruler and a pen and draw the line. Or it could have been those 2 points. Or it could have been those 2 points. Any 2 points on that graph is all we are going to need to draw the picture. And remember, what is that picture? The picture is the answer to this equation because it shows all xy pairs that make the equation true. And again, when I say that, I'm imagining that we know this line carries on forever in both directions, right? So it eventually gets to any pair that makes the equation true. And we can zoom out on that graph as much as we need to. We don't need to be zoomed in close, right? We could have a much wider view of that graph if that's what we needed. So next time we will look at, start to look at other techniques for how to find that graph, and a little bit more terminology and some other little interesting twists that come up.